In this video, we're going to be talking about optimization problems in Calculus 1. This is for section 4.7 out of the OpenStax Calculus book, volume 1. In this section, we talk about how to get an objective function to find a maximum or minimum value subject to given constraints. So let's make some definitions. In this scenario, you'll see the definitions for the objective function and a constraint equation. The objective function is the one that you're trying to maximize or minimize. In other words, this is what we would call optimization. So for example, you may be trying to maximize the volume of a can because you're going to sell something that goes within the can. Or you may be trying to minimize the surface area of the can because that minimizes the materials need and that would minimize cost. So the objective function is the one that you're targeting, the one that you're trying to make as large as possible, such as volume or area, or as small as possible, such as surface area or cost. The constraint equation is usually an equation or equations that give one or more restrictions on the variable or variables. For example, if you are trying to minimize the surface area of a can to hold something like beans, then you know that the can has to have a non-negative height and a non-negative radius. If it's shaped like a cylinder, the radius has to be strictly greater than 0, and the height has to be strictly greater than 0. It doesn't make sense to have a can that has 0 height or negative height. So those provide constraints on the objective function, which was surface area. Let's take a look at what the method would be to solve these, and then we'll look at some examples. Now you see the method in front of you. The method to optimize an equation is to use the constraint equation to rewrite the objective function in terms of one variable. In other words, using the constraint, you're going to replace one of the variables in the objective function. The one that you want to replace or get rid of is the one that's easier to solve for. The second step is just to find the interval of interest for the variable that's left in the objective function. If you're looking at radius of a can, you may get that the radius has to be greater than 0 and less than 5. This means that you're looking for the absolute maximum and minimum between the interval from 0 to 5. If necessary, you'll check the endpoints of the interval. If you're trying to minimize surface area or maximize volume of a cylinder, such as a can, then it wouldn't make sense to check the radius being 0 because that would not actually be a can. So you wouldn't need to check that endpoint for a maximum or a minimum, but you would need to check the other endpoint, which would be at 5. Let's take a look at an example so we can see how to apply this method to an actual problem. This is problem 315 out of section 4.7 out of the OpenStax textbook. Let's read the problem first to get a vague idea of what the problem is about, just as we did for related rates. Then we'll apply the same technique we use for related rates, breaking down the words a few sections at a time, using prepositional phrases, subject phrase, verb phrase, subordinate clauses, punctuation, conjunctions, etc., to translate the words from English into mathematical symbols and into a drawing. Here's the problem. To carry a suitcase on an airplane, the length plus the width plus the height of the box, or the suitcase, must be less than or equal to 62 inches. Assuming the height is fixed, show that the maximum volume is given by h times the quantity, 31 minus half of h, quantity squared. What height allows you to have the largest volume? The first time you read the problem, you're only trying to get a vague idea of what kinds of equations might be involved. In this particular situation, I know I'm looking at a suitcase, and I know I have volume, and I'm measuring how long the suitcase is, how wide the suitcase is, and how high the suitcase is. we can assume that the suitcase is basically a rectangular box shape. You need to be able to assume this in order to solve the problem, but note that that information is not given in the words itself other than the single word box. Let's go back now that we have a vague idea of what kinds of equations might be involved, and let's start breaking down the words. Remember, you're looking for prepositional phrases, subject phrase, verb phrase, punctuation marks, subordinate clauses, anything to break apart the words in English. That's about every 2 to 3 words you need to pause and see if you should write something down. To carry, okay, nothing to write there. A suitcase. In this case, we might want to go ahead and draw a suitcase, which in our case would be something looking like a rectangular box. So assuming that our suitcase looks something like this, and we've got, oops, my suitcase didn't really come together too well, so let me see if I could do a better job with a suitcase. All right, take that one off. So coming back and coming over, there we go. There is our suitcase. So let's continue with the words. On an airplane, again, not necessary for the suitcase. The length plus width plus height of the box. Now for that, I need to put labels on my picture. So I'm going to call this the length, I'm going to call this the width, and I'll call this the height of the box or the suitcase must be, okay, now wait a minute, it said length plus width plus height. Maybe I need an equation. Length plus width plus height must be less than or equal to, okay, that would be this symbol, 62 inches. So I can write that down. Next sentence, assuming, okay, a height is fixed. What does it mean by the height is fixed? Saying that the height is fixed means that height is a constant. It means it's never going to change. If anything changes, it will have to be the length of the width because the height's not going to change. Show, okay, that the maximum volume, okay, I need the volume of my box. Well, I know the volume of this rectangular box is length times width times height. But the words also say that the maximum volume is, and they give me a different equation, equal to height times the quantity, 31 minus half of the height, and I'm going to use an uppercase H since that's what I have in my picture, squared. Okay, I need to show somehow that these two equations on the left and the right here are actually equivalent. Last sentence. This is where they're actually giving me what they're looking for. What height, the height, remember, is a constant. What height allows you, okay, to have, got it, the largest volume? I'm looking for the height, but what I'm trying to optimize is the volume. And the key word here is largest. Largest, smallest, greatest, biggest, tiniest, littlest, least, most, all of those are words that indicate what's being optimized. The largest volume means optimized volume. So we're going to write that down. Optimize volume. All right. Now I need to decide what my constraints are and what my optimization equation is. Since I'm trying to optimize volume, that means that volume is my optimization equation. So now I can write that my optimization equation is going to be given by volume is length times width times height. And I'm trying to show that when I'm done, that it actually is equal to that. And I'm trying to find the height that creates that equation, right? So here's my optimization equation. What would my constraints be? Looking back at the information I was given, I have one constraint here in the first equation that the length plus the width plus the height must be less than or equal to 62 inches. I also have constraints implied by the situation and by that constraint equation, but they were not written in the words. Basically, if the length plus the width plus the height have to add up to something that's 62 inches or less, and I know that in order to have a real suitcase, I know that my length has to be greater than 0, and my width has to be greater than 0, and my height has to be greater than 0, then that means that all three also have to be less than 62 inches, because the three added together have to be 62 inches or less, so individually each one must be less than 62 inches. So this gives me four constraint equations: that the length, width, and height are between 0 and 62, and that the sum of the three is less than or equal to 62 inches. Now I need to do something to replace a variable according to our method that was given above. We need to use one of the constraint equations to rewrite the objective function in terms of one variable. We want to choose the easier variable to solve for, or the one that needs to be left in the equation. Remember that we were given that h is a constant, and that we need to show that the volume here, length times width times height, is equal to this. You can see on the right that I only have height left. That means that I need to take my constraints and I need to leave the height in there, which means I need to get rid of my length and my width. Since we can only get rid of one variable at a time, we need to choose whether to get rid of the length or the width. I've chosen to get rid of the length by solving for length, but you could just as easily have gotten rid of the width. So what do I mean by get rid of the length or the width? Let me show you. Scrolling down, I need to add another page. Hang on. I was given originally that the three added together have to add up to be less than or equal to 62 inches. So I have length plus width plus height is less than or equal to 62. But remember that h is not a variable. H is a constant. That means that I can ignore it in all of these equations and think of it as only a constant, not a variable. So I'm going to solve this for L. That means I get L on one side by itself, and that means I have L has to be less than or equal to 62 minus W minus H. Now I'm going to rewrite my volume equation and substitute out for L. So volume is length times width times height. And if I replace L with what I have here, then I can end up with, and I'm putting the H at the front since it's only a constant, times W times 62 minus W minus H. Now, if we multiply these together, we should end up that the volume, and again, this is going to be an inequality, that the volume is going to be less than or equal to 62 HW minus H squared W minus HW squared. Again, notice only W is a variable and V as well. The H is a constant. Because I have this equation now, I can take the derivative of the volume with respect to W. This will let me find the critical values, and once I have critical values, I can determine whether I have a relative max or a relative minimum. Again, we are trying to optimize volume. We want the greatest volume possible so we can pack more stuff in our suitcase. So now I'm going to take the derivative of volume with respect to the width, which would give me 62h minus, again, h is a constant, so this gives me h squared for the middle term. W is not a constant, it's the variable, but it matches the differential. So I just do a normal power rule, 2hw. This is the first derivative. Now to find the critical values, remember there are two places to locate critical values or critical points, and that would be one, that the first derivative is equal to 0, or 2, the first derivative does not exist, but the function does exist. In this case, this particular derivative given up above, which I've now underlined in green, it is defined for all values of h and w in the domain, basically that h and w are strictly positive. So we won't get any from this second possibility here. They all have to come from the first derivative equal to 0. Let's set that equation equal to 0 and locate those critical values. 62h minus h squared minus 2hw equals 0. And again, the only variable that I have is w. So I'm going to solve for w, and when you're done solving for w, you should end up with the following. Move the 2hw to the right side of the equation, and then you can divide both sides of the equation by 2h. When you divide, it looks like I lost an h there, 2h divided by 2h. When you divide, this should give you that the only critical value is given by 31 minus 1/2 of h. If you scroll up again, you will see that this was one of the expressions involved in the volume that we were trying to prove. Right here, you can see that 31 minus 1/2 h, and that's from the width, and here's the h, but it's in this one twice, which must mean that the length is the same. But we haven't proved that yet. The word show means we have to prove it. So far, all I've shown is that there is a critical value here, but that does not mean that just because it is a critical value that it has to be a maximum or a minimum. It could be a saddle point on the graph. So now I'm going to use the second derivative test and see if that will let me decide whether or not that is an extrema value. For the second derivative test, remember that you take the second derivative and plug the value in and see whether or not you have a positive, which means it's concave up, which would mean that it would be a minimum, or negative, which would mean it's concave down, which would mean it's a maximum. So coming up above, let's take a look now at what we had for the first derivative. The first derivative was 62h minus h squared minus 2hw. I shrink my page just a little bit so I can get it all on here at the same time. My second derivative of the volume, again with respect to w, would be the derivative of this equation with respect to w. H is a constant, so 62h is a constant, so the derivative is 0. H squared is a constant, so the derivative is 0. The derivative of negative 2hw would just be negative 2h, but h is a constant. What does that tell us now? Scrolling back up, this basically means that negative 2h is always going to be negative. Because it is always negative, this means that my second derivative is always concave down. If it's concave down, it has to be bent like this, which must mean that that critical value there must be a relative maximum. That means I have a maximum here at this value, so this becomes a relative max. Since it was the only one I've got, it's got to be the absolute maximum as well. Now that I know that's the relative maximum, how can I find the length? To find the length, go back to the equation where you got rid of length, which was up here at the top. Up at the top, I said the length has to be less than or equal to 62 minus w minus h. Let's come back down to the bottom and write that down again. The length had to be less than or equal to 62 minus w minus h. We need to know what the length is at that critical value, which is where we have a relative maximum. That value is given here, also arranged now in a blue rectangle. Replacing the W with 31 minus 1/2 H, I get 62 minus 31 minus 1/2 H in parentheses minus another H. By distributing the negative, this leads to 62 minus 31 plus 1/2 H minus H, which leads to 31 minus 1/2 H. In other words, the length and the width are the same values. Now to rewrite the volume, I can write that the volume, which is length times width times height, and because this is an inequality here, it must be less than or equal to the height times the length times the width, which are both 31 minus 1/2 the height. This proves the first part of this problem. Let's take a look at the words again to see if we can remember what the second part was. The second part of this problem is to find out what height allows you to have that largest volume. In other words, now that we have written our volume in terms of only the height, we will ignore the length and the width and think of only the height now as a variable, but not as a constant. The second part of this problem requires you to think now only in terms of the height affecting the volume. Let's write the equation again so that we can figure out how to maximize the volume. So the volume is going to be given by the height times 31 minus 1/2 of the height, quantity squared. If that's our equation, the question now is, how can I maximize the volume? What height would give me a maximum volume? And the answer is, to find that maximum, I need to again go ahead and take the derivative of the volume, but this time with respect to the height. So let's take a look now at our equation and see what we can do to solve the rest of this. In order to do this, we could apply the product rule to this expression here with the chain rule, but it might be easier to go ahead and multiply it out since it's only squared. That way we can simply take the derivative of each term individually. First, I'm going to square the second part, the binomial. So this gives me 31 times 31, or 31 squared. Then I get on the inside and the outside, I get a minus 31 over 2h and another minus 31 over 2h. And then the minus 1/2 h times itself would give me a positive 1/4 h squared. Multiplying all of this by the h on the outside would give me back the volume. Now the two middle terms are going to double each other so that we end up with a minus 31h. This would give me h times the quantity 31 squared minus 31h plus 1/4 h squared. I can distribute the h across now, and this would lead to 31 squared h, which, yes, if you have a calculator, go ahead and multiply it out, minus 31h squared plus 1/4 h cubed. This is our expression for the volume in a fully multiplied out form. Again, this is optional. You could have gone ahead and used the product rule and the chain rule. Now I'm going to take the derivative of the volume with respect to h, since it's the only variable I have left, and because I'm trying to find what height gives the maximum volume. First, I find the derivative, then I find the critical point. The derivative of the first term is simply 31 squared. The derivative of the second term is power rule, 2 to the front, gives me minus 62 times h to the first. Power to the front gives me plus 3/4 h squared. Now to find the critical values, I need to set the first derivative equal to 0 or look where it is not defined, but the function is. This derivative is defined for all values of h, which means that it has to be coming from the first part, which is where is the derivative of the volume with respect to h equal to 0. Setting this equal to 0, I can write in descending order 3/4 h squared minus 62h plus 31 squared equals 0. Now you can try to factor it or you can use the quadratic formula, but I think probably quadratic formula will be fastest. Go ahead and pause the video and work it out to see whether or not you come up with the same solution that I do. You can see in purple here that I have used the quadratic formula to solve this quadratic equation for h. Since this is our height, we know it has to be strictly positive. Due to the constraint on the original equation, it also must be strictly less than 62. Because it has to be strictly less than 62, this eliminates this one possibility. It cannot be 62 since the sum of the length, the width, and the height has to be 62. Thus, that means that the only critical value we get for the height is 62 divided by 3. Now we need to determine whether or not that 62 divided by 3 actually gives us a maximum on the volume. In order to do that, we will again take our volume equation, the first derivative, and we will see what the second derivative of it has. Here's the equation of the first derivative of the volume with respect to height. Now let's find the second derivative and see if we can use the second derivative test to determine whether the curve is concave up or concave down. The second derivative of the volume with respect to height on both occasions would be, that goes to 0, this becomes negative 62, and this would be 2 times 3/4 times h. Now, in order to simplify this, I could end up with negative 62 plus 3/2 h. Remember that the critical value that we got from our work up above was 62 divided by 3. We need to know when we plug in 62 divided by 3 for the height in the second derivative, do we get a positive or a negative? So now I'm going to take the second derivative of the volume and I'm going to plug in 62/3 for h. And I'm going to see whether I get a positive or a negative. By plugging this in, I have 3/2 times 62 divided by 3. Working out the arithmetic, I know that 2 will go into 62 31 times, and 3 is divisible by 3. This gives me negative 62 plus 31, which is a negative 31. Because I got a negative number, I know it has to be concave down, which means that I must have a maximum in the volume at 62/3. That means that the value of the height to give me the maximum volume should be 62/3. This completes this problem. This is actually a fairly difficult problem. Even though it is the first problem in your homework set, it is not trivial and requires you to understand a great deal about optimization. When doing the homework, you may want to skip problem 1 and go on to the other problems and come back to problem 1 when you have more experience solving optimization problems. Let's look at one that's not quite so difficult. This is problem 316 out of the textbook. Let's read the problem to get a vague idea of what kinds of formulas might be involved. It reads, you are constructing a cardboard box with the dimensions 2 meters by 4 meters. You then cut equal size squares from each corner so you may fold the edges. What are the dimensions of the box with the largest volume? Okay, first you just have a flat piece of cardboard and you're creating a box out of it. You'll have to have some duct tape in order to do this. Let's look at the picture here and see if we can understand how this picture relates to what's happening. What's happening is they're going to take each of the four corners and they're going to cut out a square. Notice that the squares will be X on each side from all four corners. When they're done, they will have a shape that will look something like the following. When they're done, then, where the dotted lines are, the dotted lines become the creases or the folds where you're going to take each side and fold it up. So that this part here in the center, now shaded in blue, becomes the bottom of your box. This is the bottom. The tabs that you see on each of the four sides become the vertical sides of the box when it's folded together. You'll have to use duct tape to connect the two corners as these will fold together and touch when you pull them vertically up. Now that we understand the situation, let's go ahead and see if we can break down the words and draw a better picture or label parts of our picture. Starting again at the beginning, you, got it, are constructing, okay, a cardboard box, got it. Box means rectangle. In this case, a three-dimensional rectangular parallelepiped or a box with the dimensions, okay, 2 meters by 4 meters. Okay, does that mean that the original box cardboard piece was 2 meters by 4 meters, or does that mean the new box is 2 meters by 4 meters? Let's look at the words. It says we're constructing a cardboard box with dimensions 2 meters by 4 meters. That means that this is going to be 2 meters on the short tabs and 4 meters on the long tabs. This is referring to the folded up box, not the original piece of cardboard. Now let's continue with the words. You then cut equal size squares from each corner. Got it? So you may fold the edges. Got it? What are, okay, the dimensions, okay, of the box, got it, with the largest volume? Something is wrong. If I had the dimensions of the box with the largest volume, do you suppose they're just looking for X? We'll need to pause here and think about whether the 2 and the 4 referred to the original cardboard or whether it refers to the folded up box. A different interpretation will lead to a different solution. It can be done either way, and I would say that these words are somewhat ambiguous, and it's difficult to tell from the words what is meant. We'll take a look at doing the problem both ways so that you can see how the answers will differ based on your interpretation. This is why the drawing and the labels on the drawing are so important. We're assuming that the box is going to be 2 meters by 4 meters, 2 meters wide, 4 meters long. The dimensions of the box are given by length, width, and height. That is what I'm looking for. But based on my interpretation, I know the length is 4 meters. I know the width would be 2 meters. The only thing I don't know is the height of the box. That must be what I'm looking for. Based on this interpretation, when I fold up each of the corners of the box, this X measure, which only applies to that length and that length there, becomes the height of the box. In other words, H is X, and we need to find X. So if we're going to do that, we need a formula for volume. The key word here is largest. Largest means optimize the volume or maximize volume. In order to come up with the constraint equation and the optimization equation, I need to think about what equations I would use for volume. The volume of this box is given by length times width times height. This will be my optimization equation. What would the constraints be? In this case, the only real constraint is that x needs to be strictly positive. If x is 0, then I have a flat piece of cardboard and not a box. If x is negative, it doesn't have any real-world meaning, so that can't be the case. Let's now see what we can do to replace the length and the width with the constants 4 meters and 2 meters to find the height. This would give me volume equals the length is 4 meters, the width is 2 meters, and the height is the unknown. If this is my equation for volume, then I can rewrite this as 8 square meters times the height. To find the optimal volume, I need to take the first derivative of the volume with respect to the height. When I take the derivative, I simply end up with 8 meters squared. This is a problem. If the derivative of the volume is a constant, then I have no critical values. This seems to indicate that our interpretation of the problem was incorrect. Since I have no variable h left, I have no way to find the optimal volume. Now I need to go back to the problem and see if I can interpret it a different way so that I can solve the problem. Starting over, it seems to me that it was my interpretation of the 2 meters by 4 meters that put me on the wrong path. Now I'm going to assume that the 2 meters by 4 meters refers to the flat piece of cardboard that I'm using to create the box, that it is the original that is 2 meters by 4 meters. That means this is 2 meters from one end to the other, including the cutout x's, and 4 meters from one side to the other, including the cutout corners. If that's the case, then I need to know what they're going to be after I cut out the corners. This side was originally 2 meters, but I cut off x on each end, which means this has to be 2 meters minus 2x, since I cut x from each side. That would make the length of it 4 meters minus 2x, because I cut x from the right and x from the left. This will give me a different equation for the volume. Based on my current interpretation, I now have that the length is 4 meters minus 2x, or the height. And you can use x or you can use h. Either one will work since x and h are the same. We'll use h just to make it consistent. And the width is 2 meters minus 2h. And then I have h. This takes and rewrites the entire equation in terms of just h. I'm trying to optimize volume, so that is the equation I'm going to be taking the derivative of. To get rid of the other variables, I had to use the information about cutting x from each of the 4 corners. Now you can either apply the product rule and the chain rule, or you can multiply all of this out first, and then you can do the first derivative. Pause the video here and take your derivative to see what your critical values will be. I got for the first derivative of the volume 8 meters squared minus 24 meters h plus 12h squared. Now we need to find our critical values by setting this equal to 0. Note that it is defined for all values of h, so the only critical values will come from setting the first derivative equal to 0. Stop the video here, find your critical values, then turn the video back on and compare your answer to mine. By setting the first derivative equal to 0, then dividing everything by 4, I was able to simplify the quadratic equation so that I could then apply the quadratic formula. Looking below, you'll see where I have applied the quadratic formula and come up with one critical value, 1 meter plus or minus the square root of 3 over 3 meters. Now this is actually two critical values, but the question is, do I have constraints on the height? And the answer is yes, the height must be strictly positive. So now I need to conclude or find out whether 1 meter plus or minus the square root of 3 over 3, whether they are both positive. If one is negative, it will not fit my constraint and I will need to throw it out. So now I will split those two up to make sure that they are both positive. Splitting it into two separate values, I am led to the following. 1 meter plus the square root of 3 over 3 meters and 1 meter minus the square root of 3 over 3 meters. Let's see what decimal approximations these are. Using a calculator, I'm able to determine that both of these are possible values for an extrema. 1.58 and 0.42 are both positive, so they meet the constraint of the equation that the height be strictly positive. Now I need to know whether I have a maximum or a minimum at these values. In order to do that, I will find the second derivative and plug in each of the values to see whether it is concave up or concave down. Remember again, going back to the original problem, that we are trying to optimize the volume. We're looking for largest volume. So when I plug into the second derivative, I hope to find a negative value, meaning that it is concave down. Coming down here to the second derivative, I will need to get that from the first derivative by taking the derivative again. Pause the video here, find your second derivative, and determine whether it's concave up or concave down using the second derivative test. If the second derivative test fails, meaning you get 0, then you will have to use the first derivative test using increasing and decreasing to predict where the maximum and minimum of the volume occur. In the first equation, you'll see again the first derivative of the volume with respect to h. I took the derivative again to get the second derivative. Notice that the h is still present. This means that I will have to plug in my two critical values into the second derivative using the second derivative test to determine whether it's concave up or concave down. If I get 0, then the second derivative test failed and I have to use the first derivative test. In this case, however, notice that when I plug in the larger of the two values, I get 8 square roots of 3 for the second derivative. Because it's positive, that means that the graph is concave up there, and this is a relative minimum. I am looking for a maximum, so that is not the one I want. When I plug in the second critical value at 1 meter minus the square root of 3 over 3 meters, the second derivative becomes negative 8 square roots of 3. Because it is negative, it is concave down, and that means it's a relative maximum. This is the height I am looking for. This means that my height, or the x value, must be given by 1 meter minus the square root of 3 over 3 meters. Now I need to find the length and the width. I know the height, I need the length and the width. Going back to the original problem, let's scroll up and see what that was. Back to our original graph, you can see that the original length was 4 meters minus 2x, and the original width is 2 meters minus 2x. Let's use those to compute our length and our width. I have now that the length is equal to 4 meters minus 2 times the height, which is 4 meters minus 2 times 1 meter minus the square root of 3 over 3 meters. By working out the arithmetic and the algebra, you should come up with the following answer. The length is given by 2 meters plus 2 square root of 3 over 3 meters. Now let's find the width. The formula for the width was given by 2 meters minus 2 times the height. By plugging in the value of our critical point where the maximum occurs, I can find the value of the width. And you should get the following value. The width is given by 2 square root of 3 over 3 meters. This concludes the second example. This is also a not trivial example, but it is not as difficult as the first one. Let's take a look at one more example and see what we can get. This is problem 343 out of section 4.7 of the OpenStax textbook. Let's read the problem and see if we can understand what kinds of equations might be required to solve it. Find the area of the largest rectangle that fits into the triangle with sides x equals 0, y equals 0, and 1/4 x plus 1/6 y equals 1. Okay, first off, this does not sound like a real-world situation. This is sort of an artificial made-up thing, but it is the kind of problem that comes in handy in solving all kinds of building and architecture problems, as well as manufacturing problems. Let's go back and see if we can break it down by looking at the subject phrase, the verb phrase, prepositional phrases, subordinate clauses, punctuation, and conjunctions. Remember to stop every 2 to 3 words and write down something on your graph or to note the information that's given. Reading the words again. Find. Okay, find something. Find what? Next words. The area. Okay, the first thing I need to do before I go any further is I need to note that I'm looking for area. Find the area. Got it. Of what? Of the largest rectangle. I will want to go ahead and outline the word largest because this is telling me what I'm trying to optimize. I want to optimize the area of this rectangle. Now I will draw a rectangle so that I can see kind of what's happening. Okay, I have a rectangle. That fits. Uh-oh, I may need to put my rectangle in something. Into, okay, the triangle. Okay, my rectangle has to fit inside of a triangle with sides, got it. X equals 0, okay. Y equals 0, okay. And x over 4 plus y over 6 equal 1. Now I'm going to note that down. Triangle sides, and then I'm going to give the 3 equations. X equals 0. If x is 0, this is just another name for the y-axis. Y equals 0. Y equals 0 is another name for the x-axis. And x over 4 plus y over 6 equals 1. This is, in fact, a line. It doesn't look like a line, but I can take this equation now and I can multiply by the common denominator, 12, to get it in a more familiar form. Multiplying this by 12, I would end up with 3x plus 2y equals 12. Solving it for y so I can get it in slope-intercept form, I would have 2y equals negative 3x plus 12, or y equals negative 3 halves x plus 6. This is the line that crosses the y-axis at 6 with slope negative 3 halves. Now I will need to draw this particular triangle and try to fit a rectangle inside of it. Let's pause here and produce the graph. Pause the video, draw the graph with those 3 as your sides, and see if your picture matches mine. Looking now at the graph, you can see that I have produced the graph of the negatively sloped line here, the graph of the x-axis y equals 0, and the graph of the y-axis x equals 0. I've made solid the triangle that I have here. Note that it is, in fact, a right triangle. Now let's go back to the words and try to interpret what we're doing. We're looking for the largest rectangle that fits into the triangle. Now there are all different kinds of rectangles that I could draw. Let me show you some rectangles that I could draw so that you can understand what we're trying to do. Since we're trying to draw the largest one, we're looking for the one with the greatest area. Let me blow up the shape of this graph so we can hone in on just the graph. By fitting the rectangle inside the triangle, they mean draw the rectangle so that it fits on all the sides. Notice that this is one possible triangle that I could draw. However, another possibility would be to have it going this way. Now, notice that these two rectangles will have different areas. The question is, which one has the greatest area? There are, in fact, many different rectangles that I could draw that would fit inside of that triangle. My job is to find the dimensions of the rectangle with the greatest possible area. Now, there are some constraints carried by this situation. When I look at this, notice that the length of my rectangle is restricted by the triangle. Obviously, the length has to be greater than 0, but it also has to be less than 4. If the length is exactly 4, to fit within the triangle, it would have to have height of 0. So this means that my length has a constraint that the length is between 0 and 4. Let's write that down below. The length has to be greater than 0 and less than 4. What else can we see from our picture? What about the height of the rectangle? Looking at the rectangle, I can see that the height of the rectangle has to be greater than 0, or again, I won't have a rectangle, but it has to be less than 6. That means that the height of my box has to be between 0 and 6, or you could call this the width or whatever you want to call it, up to you. I'm going to call it height. So I have length and height as opposed to length and width. You can do it either way. These two constraints provide constraints on the situation. Now I need to figure out again, what is it I'm trying to find? Largest rectangle's area. That means that my optimization equation is area. I'm trying to optimize the area. And the area of that rectangle will be the length times the height using the variables I've chosen. Now let's see what we can do in order to replace one of these variables subject to the constraint equation so that we can take the derivative and find critical values. In this situation, I can see by looking at the picture that the height of each box is on the triangle. The corner of each of those rectangles I drew was on the triangle, the slanted side, which is given by this equation here, now ringed in the magenta color. That means that I can replace that variable by thinking about the other one. Notice that here, when I look at these variables, length and height, that my length is given by the x-coordinate and the height is given by the y-coordinate. I'm going to replace the y-coordinate since I already have this one solved for y. So I'm going to rewrite my area equation, the length times the height, which is, of course, the same as x times y, but I'm going to replace the y with the expression from the slanted line. This gives me an equation for the area of x times the quantity, negative 3/2 x plus 6. If I multiply that out, I will get a quadratic equation in x. This gives me negative 3/2 x squared plus 6x for my area equation. In order to find where I have maximum area, I need to take the first derivative, find the critical values, then take the second derivative, determine if I have a maximum or minimum at the critical values, find the maximum, and let that be my answer. Go ahead and pause the video here and try this problem on your own, then turn the video back on to see if your answer matches mine. Let's see if your answer compares to mine. I took the equation for the area, negative 3/2 x squared plus 6, and took the derivative with respect to x. This gave me negative 3x plus 6. Since this is always defined, there will be no critical values from it not being defined. That means the only critical value must come from the first derivative equal to 0. I set the first derivative equal to 0 and solve, which gave me one critical value at 2. To determine whether it's a maximum, minimum, or saddle point, I can apply the first or second derivative test. When it works, the second derivative test is faster, but of course it does not always work. In this case, however, it does. When I apply the derivative again to the first derivative, I get the second derivative, which is -3. Because this is always negative, that tells me the graph is always concave down for the area function. That means that at this critical value, x equal 2, I must have a maximum. This is where the maximum area occurs. Since that is the maximum, now I can go back and find the y value at that maximum. Since the length should be 2, then I can find the maximum y value by plugging into this equation, -3/2x plus 6. Coming down here, I have y equals -3/2x plus 6, and I need to evaluate that when x is 2. This will give me -3/2 times 2 plus 6, which is a -3 plus 6, which gives me 3. That means that the best and largest rectangle that I can draw in that area is 2 long and 3 high. Let's take a look at our graph again and see if that looks like the largest possible rectangle underneath there. Returning to the blown up picture of the triangle, remember that we found that the maximum area rectangle occurs that is 2 wide or 2 long and 3 high. This is the rectangle with the maximum area. You can tell by looking at it that it does have a bit more area than both the red and the green, though it's not entirely clear that it is in fact larger than the blue. This concludes this video over optimization. In class, we'll do more examples and you will be able to understand how to set up and solve optimization equations.